Welcome all for the day 5 session on deep learning algorithms, and our today's guest is Mr. Abhishek Potnis. Mr. Abhishek Potnis is a PhD student in the Geo Computational Systems Lab at Center of Studies in Resources Engineering, Indian Institute of Technology, that is IIT Bombay. His research interests include deep learning for computer vision, 3D representation and reasoning, remote sensing, and geographic information systems, Internet of Things, and high performance computing. As a part of Google Summer of Earth Engine research program, he worked on the project machine learning based mapping of cropland with Google Earth Engine for identifying human-wildlife conflict locations with Center of Wildlife Studies. He has been a two-time Google Summer of Code student in the past for the organizations Celsium in 2015, where he worked on processing and visualizing three-dimensional LiDAR data from the Calypso satellite and Liquid Galaxy in 2016, where he worked on enabling Celsium for a panoramic experience on the Liquid Galaxy hardware. He is an open source enthusiast and has been a core contributor to the web browser Mozilla Firefox. Mr. Abhishek Potnis is an alumni of Vidyavardhini College of Engineering and Technology, and the computer department is proud of his achievements. Now, I, Priya Sabe, would like to extend our warm welcome to you from the entire computer engineering department of Vidyavardhini College of Engineering and Technology. Sir, I would like to hand over the forum to you.
Sure. Thank you, ma'am, for those kind words. Uh,
Thank you,
I'll,
sir.
I'll present. Yeah, I'll present my screen. Uh, yeah. Okay, we'll let this go. Yeah. Okay. Today's session, we will be discussing about deep learning, primarily from an application first perspective. So specifically, we would be touching upon the applications of computer vision and natural language processing. In computer vision, we'll be discussing the most fundamental building blocks of deep learning when it comes to computer vision, the convolutional neural networks. We'll be discussing some of the intricacies of those networks, and then we will be moving on to the natural language processing, where we will be discussing recurrent neural networks in general. Here on this slide, I have put the URL where the students can actually download these slides. Okay, so it's tinyurl.com/STTP, the short-term training program hyphen deep learning DL. With that, let's get started. On this slide, I've put together the agenda of today's discussion. So we'll be starting with what is deep learning. We'll be understanding the nuances of artificial intelligence, machine learning, and deep learning, and how deep learning sets itself apart from machine learning and artificial intelligence. We'll be understanding the prominent question, why deep learning has been popularized recently. Everyone here would be aware that since 2010 onwards, this term deep learning is gaining popularity. So we'll be understanding why now has this term been popular. We'll be discussing some of the successes that deep learning has achieved as of now in the real world with some real world applications. Then we'll be moving on to the application area, one of the application area, the focus of today's presentation, the deep learning for computer vision, where we'll be discussing convolutional neural networks. We will be talking about CNNs in detail, specifically about the convolution operation, the pooling operation, and so on. We'll be discussing a few state-of-the-art convolutional neural networks as well. Then we'll be moving on to the second focus area of today's presentation, the natural language processing part, where we'll be talking about recurrent neural networks. In recurrent neural networks, we'll take up some real-world applications where recurrent neural networks are currently being used in our everyday activities. Lastly, we will be like I have put together a slides of for the students to refer like after the session some URLs that I think would be relevant for them. And with that, we will be ending today's session. So let's get started with the presentation of today. So what is deep learning? From the infographic here, it is clear that artificial intelligence is the superset of machine learning and deep learning. I'm sure in this STTP, like many of the prominent speakers would have already shown you some version of this infographic here. So yeah, so artificial intelligence is the superset, machine learning a subset of AI, and deep learning is the further subset of machine learning itself. So you can see at the bottom the timeline of how these three terms have evolved. So the term artificial intelligence itself has been coined, since 1950s. So that time, of course, artificial intelligence was restricted to rule-based systems primarily. Around 1980s was when the term machine learning was coined and neural networks actually came into the picture. So yes, neural networks have been around since the 1980s. But in 2010 onwards, the deep learning term caught on, wherein the deep neural networks term was introduced, and it has been gaining popularity in the industry so far. So yeah, so let's understand what essentially deep learning and machine learning is and how different they are from one another. So like I usually like think of deep learning in this way, since deep neural networks, for instance, have been largely inspired from the workings of the human brain, right? So the neurons in the brain and so on. So taking an example of where machine learning and deep learning are different from one another, consider a small child of around 2 to 3 years or maybe 4 years, for instance, and he and she has never seen a cat or a dog in his or her life. Okay, so it is like parents or elders in the family of the child like show them the pictures of cat or a dog, or maybe introduce them to a live animal, a cat or a dog, and tell them specifically that this is a cat or this is a dog. The child in his mind, in his or her mind, remembers that okay, this is a cat or this is a dog. Okay, and when so essentially what the child is trying to do, I'll try to form an analogy to deep learning and machine learning per se. So what the child is essentially trying to do is he or she is looking at the image or the live animal in front of him or her, and trying to assign a label to that picture that is being formed in the child's brain. So when he or she looks at a cat, the label of cat is being assigned to him. So essentially the child is being trained. Yeah, so the child is being trained when it comes to understanding what is a dog and what is a cat. Now here is where the most important part, where we can understand the difference between machine learning and deep learning. The child never is told that dog has an elongated face, dog has a particular type of ears, cat has whiskers. So these are the things that set cats and dogs apart, but these things are never told to the child. Yeah, they are never explicitly mentioned to the child. The child inherently understands these features, as we term them in the deep learning terminology or the machine learning terminology. The child on its own understands this, and calibrates his or her brain to identify when a new type of cat or a dog appears in front of him. So what a child's brain is inherently doing is, or rather, deep learning has been inspired from the human understanding of the brain. So yeah, this is where deep learning and machine learning are apart. When it comes to machine learning, which has been as we can see in the slide since the 1980s, machine learning is a technique where the features are to be manually handcrafted and told to the classification component, saying these are the important features that you can use to make a decision and predict whether a particular object belongs to a certain class or no. Whereas when it comes to deep neural networks or neural networks per se, neural networks can automatically identify the features and make the predictions. So that is where deep neural networks and deep learning, for instance, is slightly different from machine learning. And that is also the reason why they have gained popularity. Because if you look at the evolution of AI to deep learning, we started off with rule-based systems. Then machine learning came into the picture, where primitive features were to be handcrafted and to be told to the classification unit explicitly. And deep learning, where the extraction part, the feature extraction part is completely automated, and the neural network completely does it on its own and takes the decision to the classification unit, and the classifier lastly predicts the outcome. So yeah, I think yeah, so I think I have conveyed the nuances, the differences between deep learning and machine learning. So having understood these minor differences between deep learning and machine learning, let's move on to the next slide. Yeah, but one thing I would definitely like to point out is neural networks have been introduced when in the 1980s too. We will be, of course, talking more about this when we dive into the convolutional neural networks part. But one thing that I would like to point out is the difference between neural networks and deep neural networks is the word deep, right? So the deep essentially means more number of hidden layers, the more number of layers between the input layer and the output layer, and that is how the term deep neural networks was coined. So deep neural networks is essentially nothing but similar, same as neural networks. Only thing is that it has more number of hidden layers. We'll be talking about the importance of these hidden layers and how and why it was prominent since 2010 in the consequent slides. But yeah, so now that we have understood the deep neural networks term and have talked a brief about deep learning in general, with that background, let's move on to the next slide, where we understand why now has the popularity of deep learning caught on, and why has this become an industry sensation as of now. So the three primary reasons behind deep learning being popular since 2010 are bigger data, better hardware, and smarter algorithms. So like at least the bigger data, yeah, at least I think all the three factors largely attribute themselves to the progress and advances that have been made in the field of technology, science and technology in general. The bigger data part can be also attributed to computing, the advances in computing and storage devices primarily in general. The better hardware part, talking about it, the introduction and use of graphics processing unit, GPUs. Yeah, so Nvidia came up with these GPUs, and they have now been an integral part of training neural networks. So this is this has been one of the driving forces behind the popularization of this term. Smarter algorithms, of course, have evolved with the advances in computing. So we'll be talking about this bigger data and better hardware term in more detail when we talk about the history of convolutional neural networks and how they have evolved over the time. But yeah, as of now, let's remember these three factors that have been the driving force behind popularizing deep learning since 2010. So, having discussed this, let's discuss some of the deep learning successes that have been, seen in the real world. So, specifically focusing on the domain of computer vision, image recognition is where deep learning has, shown excellent results so far. So in the figure here, in the picture here, you can see that the neural network, the deep neural network, was shown different objects in the image, and the neural network rightly classified or assigned labels to it. So the first picture of a mite. So you can see the other classes, the other insects or animals: black widow, cockroach, tick, starfish, and the deep neural network gave the highest probability for the class mite. Similarly, container ship in the ocean, in the sea, that you can see was uh, rightly classified by the deep neural network. Motor scooter and the leopard. So specifically talking about, since we discussed the example of animals at the onset of our presentation, so the deep neural network rightly understood what sets apart a leopard from a jaguar or a cheetah or a snow leopard and Egyptian cat. Yeah, and then it rightly classified and predicted that this image that it is being shown is that of a leopard. So this is how the magnitude of progress that deep neural networks have achieved in the domain of computer vision is enormous. So Another area that deep neural networks has made an excellent positive impact is the medical domain. So deep neural networks are currently being used by doctors, caregivers, and medical practitioners in general to assist them in making diagnosis. So of course, we cannot and we should not rely completely on a deep neural network, but then assisting part is definitely worth it. So in this case, you can see that the deep neural network has been used to detect pneumonia from chest X-rays. So and specifically, the neural network was able to confine the area that has been affected by the pneumonia. So that is how effective deep neural networks are when it comes to computer vision. Audio is another interesting application area that computer scientists all over the world are now experimenting on. So this is something interesting, like deep neural networks. Specifically, if we talk about recurrent neural networks and the prominently popularized generative adversarial networks (GANs) are being able to generate music on their own. So that is something, it is very interesting, and we'll be speaking about a part of it when we talk about natural language processing, specifically focusing on recurrent neural networks as we move to the consequent slides. But yeah, audio, the music generation part is quite exciting. So, and then there are many more such successes of where deep learning has achieved so far. So as I mentioned, generative adversarial networks, the recently, it's a hot topic right now in the domain of computer vision. So they have been able to actually generate paintings on its own. So that is something that is truly exciting. Neural networks being able to do it completely on their own. We are actually exploring the creative part of the neural network. So that is truly exciting. One of the other applications in this picture that you see is of object detection and classification. So the center the image wherein the neural network was able to identify a person, a skateboard, and a dog. And this has application across a variety of application areas. This can be for security purposes. This can be an excellent application where like a system like that can be integrated in CCTV cameras, for theft detection. We can have this deployed on drones for monitoring hostile territories and so on. Then there's this example that was recently popular about the game AlphaGo, where deep neural network based AI was able to defeat a player, yeah, in this game. So yeah, so far deep learning has proven to be excellently effective for the real world scenarios. So moving on to the focus area of today's presentation, specifically about the computer vision. So deep learning for computer vision. So when we say deep learning for computer vision, so the machines have so far have a great track record when it comes to these four tasks that you see on your slide right now. So those are classification plus localization, object detection, and instance segmentation. So let's start from the left hand side, and we'll move gradually towards, we'll cover all these four. So talking about classification, the example that we discussed at the initial stage of our presentation about the cats and the dogs part. So the neural network is rightly able to identify what object an image contains. So it can be a cat or a dog. But we should, like, this is worth noting that a single label is assigned to the entire object. So that is what classification is all about, right? But then, computer scientists over the world thought that, okay, it is good that an image is being labeled as a cat, but we would like to find out where in the image is the cat exactly. So that is where localization comes into picture. So deep neural networks again prove their efficiency for localization too. So in the second image that you see, the bounding box has been drawn about like around the cat, and so we know that this part of the picture is where the cat is. So that is the classification and localization task that deep learning has achieved for computer vision. Moving further, object detection. So object detection is, so you might say that object detection and localization are somewhat similar, but object detection is primarily used when you have multiple objects or multiple classes in an image. So as in the image you can see there are three classes, yeah. So there are two cats that we can see, there is one dog and there is one duck. So they have been color mapped for the sake of understanding. So you can see cat, dog, and duck have been rightly detected in the image. So moving further, instance segmentation is another exciting application when it comes to deep learning for computer vision, wherein we further push the envelope and we further try to say which part or which pixel of the image is actually a cat. So when it comes to instance segmentation, there is another good application called semantic segmentation. It is more or less similar, but in semantic segmentation, the idea is that you assign each and every pixel in an image a particular label. So instead of detecting cats, dogs, and ducks, we label the entire image. So in this case, maybe some green grass, something at the background, maybe it is a wall. So all these pixels will be labeled into different colors. So that is semantic segmentation. So yeah, on the onset, if you see these four applications, these four tasks, tasks is a good term to use. So these four tasks have been proven to be excellently achieved or implemented by using deep learning for specifically targeted for computer vision. Now when we talk about deep learning for computer vision, the discussion is definitely incomplete if we do not talk about convolutional neural networks. So convolutional neural networks are a specific type of neural networks that work excellently well when it comes to deep learning for computer vision. So let's look at that. So I have put an image of a deep convolutional neural network for you. So I'll be discussing more about each of these blocks in detail. But as of now, it will be good to note that uh, the input is in a 2D 2D two-dimensional array of a car, and the output is just a label saying that this entire object is a car. So the example that we have been discussing from the start, whether assigning a label to an image. So this is what a convolutional neural network, an end-to-end convolutional neural network looks like. So so the idea of a convolutional neural network is extracting the features from an image, and spatial correlation is something that is captured nicely using a CNN. So of course, the layers that are stacked together are convolutional convolution layer. The convolution operation is performed in this, the pooling layer, and uh, uh, on the right hand side you can see flattening, fully connected, and the softmax. So we'll be talking about it, but the feature learning part of it, when we discussed about the child and the that example of a child trying to identify a cat or a dog, the feature extraction part of it is nicely identified in this particular picture. So this part of it, the convolution layer, the pooling layer, this is where the feature extraction actually takes place. And the flattening, fully connected, and softmax is the part where the classification or the decision making from the extracted features takes place. So yeah, softmax is just another activation function that is used uh, when you have a multi-class classification problem that you wish to solve. So to give like an overview of the softmax function, I think the best way to put it is that softmax essentially predicts numerical or quantifiable probabilities for each label. For instance, it could say like car, it essentially quantifies the confidence of the neural network. So it will say car, I can say that this is a car, I think this is a car with a probability of say 0.7% or 0.7. Yeah, the truck, I think it is 0.1. So all these probabilities together, when you add it, the sum would be 1. And so what we do is essentially we take the maximum label, where we take the maximum of these probabilities and output that particular label. So if the car is having a maximum probability as the output of the softmax activation function, then we say that the label is a car. So I can understand that this image can be overwhelming at the start, but yeah, we will be discussing like I think I'll be talking about more about the convolution operation, the pooling operation in detail as we move to the consequent slides. But one thing that I would like to make it clear is that I will not be going into the mathematics of this as for this particular presentation. I would be talking more about the application area and the intuition behind understanding how actually and why the convolution operation works well. So the term, the phrase that you should understand, you should have an intuition why a particular technique is being used in deep neural networks is famous is a famous quote by Professor Andrew Ng, who is a prominent researcher in the area of computer vision. So let's dig in into the convolutional neural networks and understand the convolution operation. As you like in the last slide itself, we discussed that the convolution operations is repeated or stacked in the neural network. So what is the objective of the convolution operation? So the essential objective is to extract important features from the image and reduce the image into a form which is easier to process. So when it comes to images, you can have extremely large images, and it can take some amount of time if we tend to use the entire image for understanding the contents of the image. So the idea is that you reduce the size of the image. So if we go back to the diagram here, you can see how the size of the image is gradually reducing as you move towards the right. So that is one of the objectives of the convolution operation, to extract important features and to reduce the image in size. So the graphic here, the GIF here that you see, is not a mathematical operation, but rather you can see how the window, the black portion that you see, that is being overlaid. So let's understand the blue portion that you see is the image, and the greenish blue 3x3 matrix that you see over here is the extracted features. So you can see how each of these like if 0x0, 0x1, 0x1 each of these elements in this 3x3 matrix is being populated by looking at a 3x3 window on the image. So essentially, in simpler terms, if we can put this, what we are trying to do is the 9 elements in the image are being translated to one element in the 3x3 matrix. So this is how, this is the intuition behind the convolution operation. We'll be talking about the mathematics of it, not getting into much details in the next slide. But yeah, this GIF, I really liked it because it summed up nicely the intuition behind the convolution operation. So moving ahead. Okay, yeah. So this is a similar thing that was similar operations, the same operation essentially that was happening in the previous slide, but here the numbers are involved. So essentially what is happening is the yellow or the orange portion that you see, that is being translated as a window over the image, and the convolved feature is being populated at the same time. So an important thing to note here is the small 101, 010 and 101, the 3x3 orange block, the small letters in red that have been written here. So they constitute the kernel. The kernel, the kernel, as it is called, kernel or a filter. So these are the two terms that are interchangeably used when it comes to deep learning. So these are the filter or the kernel that is to be used to compute a convolved feature by looking at the image. So using this kernel of 101, 010 and 101, so this has the kernel, the convolved feature is computed. So that is the essence of the convolution operation. So this is like getting really into the details of the convolution operation. So as you may already know that an image that we see is constitutes of 3 bands: the red, green, and the blue. So bands or channels as they are termed. So the input channel red, green, and blue are essentially separate two-dimensional 2D arrays that you can see here, and the kernels or the filters so that I was talking about in the previous slide are here: kernel 1, which is applied to the red channel; kernel 2 applied to the green channel; and kernel 3 that is applied to the blue channel. And so what it is doing is it is trying to convolve. The convolution operation is happening. It is sliding the window of the kernel over the image. The zeros that you see, I think most of you might have noticed about these zeros. So they are the result of padding, because we wanted a well distributed like the kernel to be sliding over the entire image, and we do not want any elements to be left out. So this is because the image was of an irregular structure. So that is like getting really into the nitty and gritties of the CNN. But yeah, and that is about that. So you can see how let's talk about this. So -11101 -1011 was the kernel or the filter that is being applied to the red channel, and using this actually the output convolved feature is computed. So this is how the convolution operation works. So the primary essence of the operation is extracting the important features, yeah, of course, in a quantifiable numeric form, and at the same time reducing the size of the image. So that is where the filters come into picture. One thing worth noting here is that there can be a number of filters, on different stages of different layers in a convolutional neural network. So maybe as you go deeper, the number of filters, like it completely depends on the one who has designed the neural network. So whatever gives better results. So we'll be talking about it more, like the number of filters is an important factor when it comes to the performance of a convolutional neural network. So we'll be talking about that in a bit. So yeah, as of now, like the important point that I wish to drive home is, the objective of convolution operation should be clear in the minds of the students. So with that, let's move on to the next operation, the pooling operation. So I'll quickly, backtrack to the slide here. So you can see that each convolution plus activation, the ReLU is the activation function here, is followed by a pooling operation. So with that sequence in mind, what does the pooling operation do? So the objective of the pooling operation is not to capture the spatial features, but to reduce the size. So this again is, in line with the one of the objectives of the convolution operation itself, but this is done in a simple fashion. So it reduces the spatial size of the convolved feature. So understand this, the convolution operation actually reduced the size of the image into a convolved feature, which is again in a reduced size, and we further, try to decrease the size. So the objective of decreasing the size is essentially to decrease the computational power required to process this data. So there are two types of pooling operations. So max pooling and average pooling are the most prominent ones. So here you can see that this is the convolved feature, and the 3x3 matrix, the black portion that is moving, is essentially trying to find the maximum of the 3x3 matrix, and populating this green box here. So yeah, so as you see that the number 3 is the maximum of this, and the last two windows that you saw, the second last window to be precise, has the number 2 that is maximum, and hence the population, the 2 number is being populated here. So this is the pooling operation. So these two, convolution operation and the pooling operation, are the essentially the fundamental blocks when it comes to convolutional neural networks. So having understood, these fundamental blocks, I think we are in a position now to discuss a real world example where a convolution neural network was used to do for a real world application. So you can see here that the handwritten number recognition is I am sure most of you who have been enthusiastic about deep learning would have already come across this application. So the MINST dataset, MNIST, Modified National Institute of Standards and Technology database. Yeah, so the MINST database is a popular database. The database essentially consists of handwritten numbers, and each of these handwritten numbers have a manually assigned label to it. So if you crane your neck to the right, you can see a subset of the MINST database here. So yeah, so these are handwritten numbers with the labels assigned to it. So there is a interesting bit of history, that goes with this particular network that you see. So this network, I think, is a variant of the LayNet, LENET. The LayNet. So the LayNet was introduced by Professor Jan LeCun, and the important thing worth noting here is it was introduced in the year 1998. Yeah, so this was among the first neural networks that use the convolution operation for the application of computer vision. So if you crane your neck to the left, you actually read the URL. So I have put the URL to the code snippet where the CNN of MINST, using CNN for the MINST classifier, is residing on the website of the Keras library. So yeah, so the history part of it. So this was it is also termed as LayNet 5. So it was the first prominent, one of the first convolution neural networks that was used for a real world application. So Professor Jan LeCun is one of the three scientists, computer scientists, who was awarded the Turing Award. I think a couple of years back in 2018. So Professor Jeffrey Hinton, Professor Yoshua Benjuo, and Professor Jan LeCun were the three scientists who were awarded, who were felicitated with the Turing Award. So the Turing Award is essentially the highest distinction, in the world of computer science when it comes to research. So yeah, so that was a significant contribution. But one thing worth noting here is this was back in 1998. Yeah, when the deep neural networks were far from being implemented. So another thing we're noting here is this network has only, I think, 5 layers if you count the input and the output layer. 1 2 3 4 5, yeah, 5 or 6 layers, but the depending on your convention, of course. So this network was popularly known as the LANet 5. So this was the neural network that was implemented then. Even today, Professor Jan LeCun's website has the MINCH dataset and some of the results where he had compared classical machine learning techniques with this neural network. So yeah, so I would definitely encourage you to explore that. And as of now, Professor LeCun is actually he holds a position at the New York University, as well as he's the he I think he's the vice president and chief AI scientist at Facebook. So yeah, so he's been like leading the charge of computer vision at Facebook as of now. So having understood like that the neural networks were introduced back in 1998, so why did it take so much time for the neural networks to be popular? So there is this famous quote that necessity is the mother of invention. So yeah, so 98 to 2012, yeah, so that was the time when it took to for the deep neural networks to gain prominence. But what was it specifically, what was the starting point that made the world notice deep neural networks? Was this particular competition. So ImageNet large scale visual recognition challenge. So this challenge has been every year this has been being organized by Stanford University, and I think Princeton University is also involved in this. So in 2012, this particular person so I think, yeah, so AlexNet, the inventor of the AlexNet is Alex. So I think yeah. So yeah. So the AlexNet was introduced in 2012 as a entry to this particular competition, and so that was the time when graphical processing units were being used, GPUs were being used, of course not for neural networks. So I think a couple of days back I read this article where so someone asked the inventor of this AlexNet, so what made you realize, or what made you use GPUs for training a neural network? So yeah, so he replied that he actually had read a couple of research articles where GPUs were being used for matrix multiplication, and I think he was one of the first persons to train a convolution neural network on a GPU. So when I said that Professor LeCun proposed the LANet back in 1998, yeah, so that time GPUs were not, of course, I think they did not exist then. Yeah, so he was limited by the technology at that time. So yeah, so the training, which is the crux of a deep neural network, was not possible to implement. So but in 2012, Alex, and I think with a co-author of his, proposed this AlexNet. They trained this convolution neural network, which is inspired or based on the LANet itself. Of course, there are some intricacies that the AlexNet introduces. For instance, the ReLU activation function, yeah, and the convolution and the max pooling operation are inspired from the LANet itself. But the innovation part of it was that they trained it over graphical processing units, reducing the training time and actually making it feasible for training the network. And AlexNet, incidentally, won the first prize. It was the best network in the ImageNet competition. So talking about the competition, the ImageNet is a large, extremely large collection of images and manually assigned labels. So like when we spoke about the examples of cats and dogs, so there are tons of images with the corresponding labels of the objects that the images contain. So like the ImageNet dataset is, I think, openly available on the web. So those of you who are enthusiastic about exploring this can feel free to explore the ImageNet dataset. So the accuracy that was achieved by AlexNet in 2012 was 84.7%. And interesting part of it is that the second person who won this competition had an accuracy of around 73%. So that big was the difference between the first and the second entry. So that is where the world actually took notice of deep neural networks because of the better hardware. The second factor, if you remember in my earlier slides, why now, the better hardware part of it, because of the GPUs, and of course some innovation, the smarter algorithms part, and the ImageNet constituted the first reason of bigger data. So bigger data, better hardware, and smarter algorithms essentially drove the popularity of deep learning. So that was back in 2012, right? So when it comes to the applications of computer vision and deep neural networks, uh, so as the time has progressed, the computer scientists over the world have tried to uh, you know uh, address the disadvantage, or some negative points of a neural network, and propose a new neural network that solves the disadvantages of the earlier one. So similar thing happened with the AlexNet. So the problem with AlexNet was, even though it was feasible, but it still took an extremely large amount of time and computational resources to train the network. So that was when in the ImageNet competition of 2014, the VGGNet was introduced. So VGG essentially stands for I think Visual Geometry Group. So it is a research group in the University of Oxford. So these people, they came up with this VGGNet. There are various variants of the VGGNet out there: VGGNet 16, 32, and so on, depending on the number of layers. But the essence of a VGGNet, and what sets it apart from the AlexNet, is VGGNet proposed the use of fixed size filters. So when I mentioned about the filters when we were discussing the convolution operation, AlexNet used different sized filters. Like somewhere it used 5 cross 5, 3 cross 3, and so on. So what VGGNet proposed was, if a fixed size filter of say 3 cross 3 was used, they were able to replicate the same effect used by AlexNet filters of different size. So with this argument, they implemented this neural network. And with the fixed size filters, I think the number of parameters that were to be predicted by the model, that were to be assigned by the model, reduced, and that greatly impacted the performance of the network. So there was a reduction in travel time, training time. And but one thing again worth noting here is that VGGNet was a runner up of the ImageNet competition. But then it caught on, because the advantage of reducing the training time is a pretty good advantage to have. So that was the reason why VGGNets have been popular. So so before we move to the next focus area of today's session, I would like to also to talk about some other networks that have been proposed. So as I said, computer scientists over the world have been trying to work on the disadvantages of a particular network, and trying to propose a new neural network that counters those disadvantages. So there have been many such networks proposed, till now. So VGGNet was back in 2014. It's to 2020 now. So there have been networks like that there's InceptionNet, there is ResNet, which address the problem of vanishing gradient when it comes to really deep neural networks. So ResNet is one thing that I would definitely recommend each of the deep learning for computer vision enthusiasts to look into. So essentially the idea is that they use residual connections to tackle the problem of vanishing gradient. So my recommendation would be to keep yourself updated of the state of the art neural networks that computer scientists all over the world are proposing. At the same time, understand the difference between a neural network that the newly introduced neural network is trying to solve, and what was the earlier neural network, like what was the working and what was the disadvantage with it. So I think we have briefly touched upon the application area of computer vision. So let's move on to the application area of natural language processing. So deep learning for NLP. So when it comes to natural language processing, I'm sure there have been much more prominent experts than me who have already spoken with you about natural language processing. But I'll try to briefly cover what I felt was best for the session. So natural language processing has been, part of our daily activities even before we know it. So for instance, take the example of the text that we type on our mobile phones. Yeah, predictive text. So what is the word that the mobile thinks which we will type next, and it predicts it for us, right? So that is one of the applications that we have been every one of us, I'm sure, is interacting it with daily. Google search is another example of natural language processing. So when you type in a word, you see the next word is being predicted. Yeah, so that is another example of natural language processing. Somewhere at the back of their servers, some complex form of deep learning is running, and yeah, so some of those application areas for NLP are that. Alexa and Google Assistant are another voice-based application of deep learning for NLP. Chatbots on the same lines, for question answering purposes. You pose a question to the chatbot uh, constructs the English sentence, keeping in mind the rules of the grammar, and of course, it should make sense. So these are some of the application areas or the domains where natural language processing, specifically deep learning, has made a huge impact. So recurrent neural networks. So of course, again, without the discussion of recurrent neural networks, deep learning for NLP, the discussion is definitely incomplete. So I'll be talking about the intuitive sense of a recurrent neural network. So in this picture that you see, so the first picture that you see is essentially the whole recurrent neural network. So it looks very simplistic, but when it is unrolled, so this is how actually it exists. So essentially, a recurrent neural network, the name itself suggests, is recurrent in nature. So the basic idea of a recurrent neural network is predicting or using the next or using the input, uh, or rather, to put it in much simpler terms, to use the output itself for the next output. Yeah, so I'll give an example. So essentially what it tries to do is, the input is made to go through a neuron. Some output is generated out of the neuron, and that generated output is again fed back to the neuron to predict the next output. So that is why, through time, if one is to see, a recurrent neural networks looks like this. So the output of the first operation is fed as input to the second operation. So naturally, these type of neural networks are best suited for data when it comes to when it is of sequential nature. So stock market is a great example of where recurrent neural networks have impacted. I think temperature predictions, like the meteorological parameters predictions based on time series data. So that is again a good application where recurrent neural networks are being used. And the most prominent and the focus area of today's presentation, the natural language processing. So an English sentence is essentially a series of words, right? So a series of words. So the recurrent neural network tries to predict the next word given a set of input. So that is how recurrent neural networks are influencing the domain of natural language processing. So yeah, when I spoke about natural language processing and the role of recurrent neural networks, it is worth noting that RNNs tend to remember the past, and its decisions are influenced by what it has learned from the past. So as I said, the next word is predicted by a RNN is influenced by what earlier words it encountered. So the main strength of RNN is the capacity to memorize the results of the previous computations and use that information in the current computation. But one thing worth noting here is that vanilla recurrent neural networks are not known to memorize long sequences of data. So that is where the two variants, and the two most popular variants, I must say, have come into the picture: the long short-term memory (LSTM) and the GRUs, the GRUs. Yeah. So so essentially, both these LSTMs and GRUs have in them are gates. So to remember extremely large sequences of data. So I think we have fairly talked about CNNs and RNNs. So one thing that I would like to explicitly mention is that convolution neural networks are known to work with a fixed input size. Yeah, whereas recurrent neural networks are known to work, they do not have this constraint. So the input size need not be fixed, because the reason being they work with sequence of data, right? So an English sentence will not necessarily have, say, 10 words. Different English sentences can have different words, and that is, that is why it is best suited for natural language processing. So having understood this, another application that recurrent neural network is extremely successful at is machine translation. So by machine translation, I want to say, like, the language translation, English to French, for instance. So a variant of this vanilla recurrent neural networks is prominent, as I mentioned, LSTMs. So I would recommend, there is this paper on NMT with attention, neural machine translation with attention. So the attention part of it is essentially trying to, assign weights on the words, that the neural network will predict in the future. So as an example here, in the picture you can see the sentence "I am a student" has been, rightly translated in French as saying "Je suis étudiant." So yeah, so essentially these neural networks are excellent when it comes to these type of neural networks are excellent when it comes to natural language processing, specifically the machine translation part. So if you crane your neck again to the right, I I don't know. I am not apologizing. I think that I think I put this to, break the monotonous nature of the presentation, so that you get at least some good neck exercise. So if you crane your neck to the right, you can read the URL. It is a TensorFlow tutorial with the NMT with attention. So yeah, you can, you can run this in the Google Colab notebook, and you can yourself look at the results of how good the machine translation works. So talking about this, the best part is, the data set that the simplicity of the data sets that these neural networks consume. So for English to French translation, the data set is essentially a 2-column data set, with the first column being the English sentence and the second column being its French translation. So if such a data set is provided to a neural network, for example, the neural machine translation with attention module, it will, learn to translate English to French. So I'll definitely recommend the students to, run this tutorial and experience the effectiveness of this neural network at first hand. So yeah, I think we have talked quite a bit about CNNs and RNNs, and this was a bonus slide actually I have introduced at the end. So this is an interesting upcoming research area that is prominent nowadays. So the image captioning. So we are expecting a neural network to construct in English language what it is actually looking at. So the task, mind you, is difficult, but so show and tell image captioning system was proposed by Google in, I think, back in 2016. Yes. So what they essentially did was, they coupled a convolution neural network with a recurrent neural network. So of course everyone here listening might already have assumed, like, rightly assumed, that the data set to such a neural network would be pairs of images and a corresponding English sentence. So for example, the image that you see on the left, so it's like a market, and people are selling the vegetables. So this image is coupled with the caption of like an English sentence that is transcribed manually. So a group of people shopping at an outdoor market, and so of course in this example, this is being shown as the predictive or inferencing part of it. So, but I'm talking about the training. So that is how the training data set for such a system looks like. So yeah, that this is essentially, so my whole point behind showing you this application of image captioning is how CNNs can work with recurrent neural networks. So essentially, at its core, what this system is trying to do is the image features that the convolution neural networks have captured. It is trying to map those image features with the English sentences. So that is where recurrent neural network comes into picture. So this is how, and this system is working quite well. And of course in 2020 it's been 4 years since the system was proposed. So I'm sure by now this would definitely have improved a lot. I think one of the, like, it just came to me. So in Facebook, if you see, sometimes if you are a coding enthusiast, so the images, the photos that you upload, so if you look at the source code of a Facebook page where you are seeing a photo, in the source code you will see there is this ALT ALT alternate attribute in the img tag of HTML. So there actually Facebook is applying this image captioning. So if there is a photo where a group of friends of yours and you are standing, so the ALT attribute will actually have the description saying six people are standing, and maybe describing about the background. So slowly and steadily, Facebook is also, I think, trying to test this feature, and maybe at a later point of time they would like to inculcate this to give a better user experience. But yeah, so like big technology giants around the globe are now focusing on the image captioning problem for this. So yeah, I think with this, I have like briefly touched upon convolution neural networks and recurrent neural networks. So I have put this slide, like I mentioned in the agenda, where do I grow from here? Where do I go from here? So these are some of the URLs that I felt would be relevant to the students, yeah, after this session. So those who are enthusiastic about learning more about applications for computer vision or natural language processing, so they could look at these URLs. The Google's crash course on machine learning is I think a good starter if you have some background of machine learning. It is a good refresher, I would say. Like the terminologies, it refreshes the terminologies that you already know. The Coursera specialization is definitely, I think, a good recommendation. And the CS230 certification is also recommended.
Hello, Abhishek. Hello, Abhishek. Hello, Abhishek.
Hello.
Hello, Abhishek. Yeah,
Hello.
Abhishek.
Uh,
Yeah. uh,
Hello. Hello. Hello.
yes, Abhishek.
Ma'am, can you hear me? Hello.
Uh, Not very clearly, Abhishek.
Okay, ma'am. I'll switch the Wi-Fi network then. Yes, ma'am.
Okay.
Hello, hello.
Yes, Abhishek. Yes.
Yes, ma'am. I think I'm on a different network now, ma'am. I'm very
Huh.
sorry, ma'am. This internet
And no,
actually.
no problem, Abhishek. You'll
Uh,
have to again share your screen.
sure, yes, ma'am. Yes, ma'am. Ma'am, I think I talked with Swapna, ma'am. So she said I was on the references slide. So I'll start from there.
Fine, fine, fine.
Yes, ma'am. Ma'am, are you able to see my screen?
Uh, 1 second. Huh.
Yes, ma'am. Ma'am, now I'm on the presentation mode now.
Yes, I able to see. Yes.
Yes, ma'am. Okay, ma'am.
Continue, Abhishek. Huh.
Sure. Sure. Hello. I'm really sorry for the I'm really sorry for the interruption. Actually, my internet had some issues, so now I've switched to a different Wi-Fi network. So yeah. I assume my voice broke off from this presentation from the references slide. So I'm not sure exactly where at what point my voice broke off. So essentially, I've put together these URLs for the students to refer after this session. Uh, so one thing, these URLs, the machine learning course crash course from Google is actually a good refresher if you have some basic knowledge of machine learning. The specialization of on Coursera for deep learning, I think, is a must. Yeah, it's very good. It is taught by Professor Andrew Ng. I think most of you would already be familiar with him and his courses online. The 231N deals with the convolution neural networks part, and the 224D of Stanford deals with the natural language processing for deep learning. So these are the I think prominent courses on the web that you can that are freely available, and you can learn from them. The other references of CNN and recurrent neural networks are some good blog posts that I found that are a quick refresher for you to look at. So in addition to looking at the courses and learning from the videos, what I would personally recommend is that you like select a problem and then try to work on the problem using these tools. So for instance, my research area is satellite image processing for my doctoral thesis. So my problem that I'm trying to work on is detecting buildings in a flood scenario, or detecting damaged buildings in an earthquake scenario. So when I say a flood scenario or an earthquake scenario, we work with images that are captured by satellites. So this is a very specific application area and a problem that we are trying to solve. So I think that should ideally be, like, from my personal experience, I think starting from a problem and then working your way using the tools, implementing it, yeah, writing the code yourself, and then understanding the intricacies of the mathematics involved, and the implementation details. I think that is a good way to learn, and learn in a better way, I would say. So that the interest of yours is, I think, reinforced when you look at this from a application perspective. So yeah, I think that I think that from my personal experience, I can definitely tell that it works. And so yeah, I think so. We have briefly talked about recurrent neural networks and convolution neural networks, the application areas being computer vision and natural language processing. Uh, I think, yeah, so that's all from my side. So yeah, I think I'll end my presentation here. So thank you very much. Hello, hello, hello.
Yeah, yes, Abhishek. Yes. Hello.
Hello, ma'am. Ma'am, I have
Yeah.
yes, ma'am. I have
Huh.
reached the last slide, ma'am.
Okay. Okay. Abhishek, there are some questions that if, I mean, can you answer them?
Sure, ma'am. I'll stop sharing my screen, and
Huh. 1 second.
uh, yes, ma'am.
I
Ma'am,
will
I'm on
put it
the
on.
yes, ma'am. Sure, ma'am.
I'm just searching the chat box. There were questions.
Sure, sure.
Okay, I request participants, if they have further questions, please put it in the chat box. I think Abhishek, the question is deleted. The person has deleted the question from the chat.
Okay, sure, ma'am. No problem, ma'am.
Okay. Okay. There's one question. Can you see that on the screen?
Yes, ma'am.
Yeah.
So the question is, what are the current research trends of deep learning and machine learning? Well, the current research trends will of course depend on. Hello, yeah. So the current research trends will depend on the application area we are talking about. So when it comes to computer vision and natural language processing, I think these are the two application areas that definitely are currently popular nowadays in the industry, and that is the whole reason why we are having this STTP on natural language processing and deep learning. But then, in the vast area of computer vision, there are specific areas that are currently, of prominence. For example, like for like it can be like in the domain of multimedia images, as well as it can be in the domain of other types of images. For instance, the satellite images that we at our lab work with. So yeah, so deep learning for computer vision and NLP again, as I already mentioned in my presentation about the Google Assistant, the Siri, and from Apple, and other such voice assistants, for that matter, the chatbots. So yeah, NLP and computer vision are at this stage extremely relevant when it comes to the industry, and so at this stage, I think the industry too is beginning to evolve and adapt by trying to inculcate the experts on these domains into their firms, and trying to use or leverage the technologies built on these research areas for uplifting the user experience of their customers. So yeah, I think that should answer your question.
Yeah, I don't see any other questions in the chat box.
Sure, ma'am.
Uh, so, so I request Priya, can you conclude the session? Priya ma'am, can you conclude the session, please?
नहीं मैं हूँ उसमें Thank you, Abhishek. Session was very informative. I appreciate the efforts taken by Abhishek to conduct this session. Thank you, everyone.
Thank you, ma'am, for this opportunity to speak to this audience. Thank you. I'm very grateful for the opportunity. Thanks a lot.
Thank you.
Thank you.